Hello, multivariable calculus students. This is Mr. Johnson, and this is section 12.7, which is on triple integrals. And the initial triple integral is not quite as bad as I think what it most likely sounds like. This is just essentially a double integral, but then we add that third integral with that third variable, but the operations are really similar to what we did with double integrals. So the the types of objects that we're integrating over, those are kind of the complicated parts, and knowing what order makes the most sense with regard to the integration itself. Do you do the x's first and then the y's and then the z's, or which order makes the most sense? Okay, so just as a quick overview, remember when we had back in single variable calculus, we had our just single integrals, like an integral from a to b of f of x dx. That's going to really give us area underneath that graph. Keep in mind that if you do like the average value calculator, and I'm not going to get into all of this in great detail, but sometimes an integral, if it's utilizing like the average value of a function, that will be actually a function value rather than the area under the curve. So there are other iterations of a single integral, similar to double integrals. So a double integral, over some region D, let's say, that is typically the volume. However, we started to see, and we will continue to see, how a double integral could produce area, such as surface area, for example. So a double integral doesn't necessarily give volume, but it often gives volume. So what does a triple integral give? Well, a triple integral gives the hypervolume, or something that we are unable to really see in space, given that there are actually four variables. However, a triple integral can also give us the volume depending on the situation. So we'll talk about that as well. So they all sort of have connections to each other to a certain extent, but triple integrals is just now the next level. The region, so let me back up. So in a double integral, the region we integrate over is D. It's going to be some area on a plane. So with a triple integral, we integrate over space. So for example, this first definition talks about the box B that we integrate over. So again, with a double integral, we integrate over a region on one of the planes. A triple integral, we integrate over a three-dimensional object because of the variables that we're utilizing. We're utilizing x, y, and z in our integration. So we're integrating over a box or a three-dimensional object. You could call it anything you want. These definitions that we have initially here are talking about a cube or a box that we're integrating over, just for the, I guess, sake of understanding what the formation of the integral is. And I'm not going to get into great detail with this right now, but you can see that as you look at a box in space that you're integrating over, you could separate out this larger box into little cubes, okay? And each cube has a change in x, and it has a change in y, and it has a change in z. And obviously, the goal here would be to make these little cubes really, really, really small so that you can get a really accurate estimation. That's where integration comes in. So again, going back to the last couple of years, you integrated with rectangles with Riemann sums, this infinite rectangle, in order to get the area. With double integrals, we did volume, and so we used these infinite columns. And so now what we're doing is we're talking about using these infinite cubes that we are analyzing as the change in x and the change in y and the change in z. Now, all of those are based on this larger function, f of x, y, z, which again, don't try to picture this because it might hurt. You can't. It's a fourth variable that we are unable to physically graph right now, and so therefore it doesn't have the same application as a double integral. Where we can see it in a double integral, it's the volume underneath the surface that's relatively easy to even graph or to see on a graph. This is not, and so you have to just go with the same process of development, and that's what this triple integral is going to define. Now, the order that we see in this definition is dx, dy, dz. You can sort of brainstorm here for a second. There are 5 other orders. You could switch these 3 up in any particular order, which again would be a total of 6 complete orders. This would be one of them, so there are 5 other ones, and we'll talk about that stuff in just a little bit. Okay, let's try an example, because again, that often will sort of help us identify the strategies and the process. So we're doing the triple integral over a box, which again, all that really means is that x, y, and z are going to be bound numerically. And so in more or less, this is sort of just a simple integral setup. I'm just going to write this the way that I see it. So it's going to be x first, and then y. Oops. And then z. And you could do that in any order, by the way. The function is xyz squared, and the way that I set it up is dz, dy, dx. But again, you could set it up in the order that you see above in the definition if you'd like. Okay, so we're basically just integrating this as we would have a double integral. We just have that third integral in there, and additionally, this one can actually be separated because each of the x, y, z squared, all of those are being multiplied, and each one is numeric. So we could sit here and set up separation of integrals and multiply the results. And again, this can occur in a situation like this where it's more of a straightforward integral. Okay, so we take a look at the first one. Antiderivative is 1/2 x squared. That's evaluated from 0 to 1. And then 1/2 y squared, evaluated from -1 to 2. And 1/3 z cubed from 0 to 3. So if we perform all of those operations, we get 1/2 for the first one, multiplied by the second one is going to be 2 minus 1/2. And the third one is going to be 9. So in the end, this gives us 27/4, and that's your first example. Okay, so let's talk about what we consider a type 1 region. Now, again, we talked about type 1, type 2 kind of stuff in the last, with double integrals in the last couple sections. This language is not something that is universal. So if you look at another textbook, go to a different university, talk to a different professor, they'll call it different things. So this isn't universal. This is just what our textbook organizes it as. So I want you to think about it. You don't have to memorize the type 1 versus type 2 versus type 3 regions. There are 3 total, but it just helps us to have the conversation at least. So the big thing here is that a type 1 region is going to have dz as the innermost of the triple integral. And what that means then is that, and I'll try to do my best to explain this, it's kind of hard to visualize. So when you are integrating over a 3-dimensional object, and by the way, we're calling this E now because it's not necessarily a box. So it's some, random 3-dimensional object. This 3-dimensional object we have to somehow define. We have to define its parameters. So the way we do this with the type 1 region is that we say that E is bordered by a function of z, top and bottom. So function z, top and bottom, function z, top and bottom. Then we have to set up the other 2 integrals, and we do that in a similar way that we did double integrals so far in this chapter, is that we project this object, so this 3-dimensional object, we project it onto the xy plane. And the reason is that z has already been used as the function parameters, both as the top border and the bottom border in space. And so we have to project it down in order to get what the x and y parameters will be. So you can see that all 3 of these are just examples of a type 1 region. And within the type 1 region, the other 2 integrals, so the integral for x and y, could be written as either x first and then y, or y first and then x. In other words, when you think about the notation here, with a type 1 region, you could have dz, dx, dy, or you could have dz, dy, dx. So there's kind of these like 2 sub categories for a type 1 region. It all boils down to what is easily defined in terms of when you look at this region that's projected. Is it easier to border this with y and then leave x as constants, or vice versa? And then the second thing is that what type of antiderivative is possible. And we saw this many times so far, is that if you do this in one order, the antiderivative is awful or impossible. If you do it in the other order, the antiderivative is reasonable and pretty fast. So it depends on the setup, which I know is not what you want to hear. You want to hear more of a concrete this is what you do, but it really depends on the problem and what is possible. Okay, let's try example 2. So example 2 says we're going to evaluate the triple integral over the region E. The function is 2x, and E is defined by the following. So let's just assume, because we're kind of in this stage, that this is a type 1 region. What that means is that we're going to either use dz dx dy or dz dy dx. All right, just one of those two. That would be considered a type 1. Okay. Then what that means is that the projection, as you can see in the figures above, the projection will be on the xy plane. Okay, so z is bordered, as you can see in our question, z is bordered by 0 and y. And so we're going to project this object E onto the xy plane in order to get a sense of what it looks like in that region. Okay, so here it is right here. And by the way, we wouldn't necessarily need to do this because we basically have all of our stuff written for us in our definition, but I want to make sure you see the visual. So if x is between 0 and the square root of 4 minus y squared, remember we had one that was identical to this in a couple of different problems actually. That's going to be the right half of a circle, and it has a radius of 2, and that's going to be x in between 0 and square root of 4 minus y squared. Now if y is between 0 and 2, that means that the region is actually just here in the first quadrant. Okay, so that's our region. If we were to like think of if you're sitting at your iPad or your paper and you're looking at this object right now, E, the three-dimensional object E is hovering above the page, and if you we're shining a flashlight on it, this is the shadow it casts on the xy plane. And so that gives us a sense of what the parameters of x and y are going to be. Now, we could write this, like I said, as dz dx dy or dz dy dx. I'm going to go with kind of the way that it's written in the problem. I'm going to set this up as the integral, and I'm going to put y on the outside. Y is 0 to 2. And then x would be 0 to the square root of 4 minus y squared. And z is from 0 to y. And then again, the function is 2x. And the way that I wrote it was like this. Now, I'm gonna calculate this one, but just for the sake of hopefully understanding, I'm gonna write it the other way as well. So if I look at this object and I want to put x on the outside, well, x goes from 0 to 2 as well, certainly, and y goes from 0. Now I got to think about what the equation for that little curve is in terms of y. So when we go back up to the original here, this is going to be let me erase this for a second here. Hold on. Okay, so if this is x equal to the square root of 4 minus y squared, that will be the same thing as x squared plus y squared is equal to 4. We've talked about that a lot. That's why it's a half a circle. So if I was to solve for y and come up with the equation of that curve that I have the arrow pointing to over here, that would be the square root of 4 minus x squared. And z is not changing, because remember, I'm not trying to change that particular order. So this would be dz dy dx. Now, does it matter? And the answer is no. This problem is essentially the same length and the same difficulty no matter which one of these I use. But both are considered type 1. One is one rendition of the order, the other is the other rendition. Okay, I'm going to go through the red one just because that's the first one that I wrote. So I have the integral from 0 to 2, the integral from 0 to the square root of 4 minus y squared, and I'm going to start with the antiderivative in terms of z, which is 2xz, and z goes from 0 to y, which gives us 2xy, and now we have dx dy. So there's your first integral. Okay, next integral. Change colors again, so we have the integral from 0 to 2. The antiderivative in terms of x would be simply just x squared y, and x goes from 0 to the square root of 4 minus y squared. Okay, so we plug in our stuff. I'll kind of take this the longer route here. So we have this squared times y, and of course if x is 0, that's 0. So that gives us 4 minus y squared, 4 minus y squared times y, and that is 4y minus y cubed. Okay, almost there. Now we have to do the antiderivative of that guy, so we have 2y squared minus 1/4 y to the 4th, and we're evaluating from 0 to 2, and that gives us 8 minus 4, which is 4. So there you go. That is an example of that type 1 where, again, it's a little bit more complicated with regard to the limits. Okay, so here's a third example, and again, the goal here is just to make sure that we have a good sense of how to do this, and I think that you see it once, that's really probably not enough. But really, there's no difference here. We're just going to set up a type 1 region, and so again, it's going to be dz dx dy, or dz dy dx, whichever one seems to be easier. We have our function, which is obviously a little bit more complex. I'm going to go ahead and just quickly sketch the region. So if we are looking at so again, we're doing type 1. Sorry, I didn't even label that, type 1. And we're going to project this on the xy plane. So y goes from 0 to x, and x goes from 0 to 1. Okay, so the region is right here. In fact, we've done regions like this already with double integrals, so that really hasn't changed. So again, you could kind of write it either way. I'm going to go ahead and write it the way it's written, which is that you take x 0 to 1, you take y from 0 to x, you take z from x to 2x, and the function is yz cosine of x to the 5th, and we have dz dy dx. So that would be one option. Again, for the sake of hopefully understanding here, I'm going to switch this around. So I'm going to put y on the outside. Y happens to go from 0 to 1 because the minimum y is here and the maximum y is at 1. Now x, and again, you can look back at our examples from earlier in the chapter, but x has an upper boundary of 1, but the lower boundary is y equals x. Because again, we're redefining this where y is our set of constants and x is going to vary. So this next integral would go from x equals y to 1. Z doesn't change. And your function, of course, doesn't change. And that would be dz dx dy. So again, in terms of the order, I don't know that it really matters. I guess I haven't tried the blue one necessarily, but I don't think it matters in terms of difficulty or speed in terms of the problem. So I'm just going to do the red one. So I have the integral from 0 to 1, then the integral from 0 to x. I do the antiderivative with respect to z. So I get 1/2 y z squared cosine of x to the 5th. Evaluated at z equals x to z equals 2x. So that's going to give us 2y x squared cosine of x to the 5th minus 1/2 y x squared cosine of x to the 5th. And I'm going to go ahead and end it there for the moment. So that's dy dx. We can combine these because they are similar terms. So 2 minus 1/2 is going to give us 3/2. So I'm just going to rewrite. Not going to do anything with the antiderivative. It's usually easiest to simplify and then keep working on the antiderivatives. Okay, so that's what I have now, if I was to just simplify that down. Okay, so now I do the next antiderivative. So with respect to y, so I get 3/4 y squared x to the 2nd cosine of x to the 5th. And y is from 0 to x. So we get 3/4 x to the 4th cosine of x to the 5th dx. All right, well, you can see that the next antiderivative is a u sub. I don't think we probably could have avoided it. I'm just going to sort of pull this out as sort of a side note, like scratch work. So I'm gonna forget about the 3/4 right now. I'm just working on the u sub. So we'll let u equal x to the 5th, and du is obviously 5x to the 4th, and we want to make sure to move that 5 over. We'll deal with the 3/4 in a moment. Okay, so I get this. So this integral in terms of u is 1/5 integral of cosine of u du, and that obviously is 1/5 sine of u. And we would convert that back to 1/5 sine of x to the 5th. Okay, so that's our scratch work with the u sub. So we'll put it all together. Again, remember that we do have that 3/4 up here. Okay, and so we'll combine all that stuff together. So what we're going to get is 3 over 20 sine of x to the 5th, and we evaluate this from 0 to 1. So our final answer is 3 over 20 sine of 1. Okay, so again, that's just another one to add to your list. That's a type 1. The way we analyzed it was a type 1 region. Okay, so let's move on to type 2. So type 2, I think naturally is more difficult for us because of the fact that, we are kind of naturally, we think of z as sort of our dependent variable. It's easier maybe for our brain to think of it that way, kind of similar to a plane. If you write an equation, you naturally write an equation as y equals something or other x, instead of writing it as x equals something other with y. So it's more natural for us to think of like the z equals first. Well, in type 2, the innermost integral, as you can see up here that I'm highlighting, is dx. And what that means then is that the rest of it is either dz dy or dy dz. So we are projecting, and again, you can go to your image here. You have this region E, this volume that you're integrating over. You're defining it by x, and you're projecting it onto the projecting it onto the yz plane. And so then from there, you have to figure out, okay, how am I going to define that little region D that I'm now going to integrate over? So that's the process. Okay, so let's start and draw ourselves a little picture of this one. It is set up for us, so I understand that. I'm just wanting to make sure we understand the process. So this is the projection of the YZ plane, and it was, it's because we start with X on the interior. Y is going from 0 to Z. So Y equals Z will be this line, or Z equals Y, however you want to say it. And so Y is going to go from the line Y equals 0 to Y equals Z, and that means that we have Z from 0 to 1. So let's say that that's 0 to 1, or sorry, let's say that Z equals 1. And so therefore the region is right here. And of course this is going to be, this will be 1 as well. Okay, so you hopefully you kind of get an idea of what that is. I don't think there's necessarily a need to switch this around. And so because of that, we'll just tackle it as it's written. We have the integral from 0 to 1, the integral from 0 to z, and we're going to take our first antiderivative with respect to x, which is just x z e to the negative y squared, where x is from 0 to y. Whoops, sorry. And that gives us y z e to the negative y squared. And then we have dy dz. Okay, in a similar way, we have a u sub that's sort of buried in here. So I'm going to just pull out, again, the z is sort of extra right now. The z is a coefficient. So I'm just going to pull out my y e to the negative y squared so that we can focus on our u sub. U is going to be negative y squared. Du is negative 2y dy. and we'll move that over to get negative 1/2 du equal to y dy. Okay, so this u sub is negative 1/2 the integral of e to the u du, which is, of course, negative 1/2 e to the u. And then we'll convert that back in terms of y. So that gives us negative 1/2 e to the negative y squared. Okay, so again, don't forget that you have a z right here. I just was working on the u sub portion of it. So now we'll kind of go back into the problem. And so our antiderivative, I have still this integral 0 to 1, but our antiderivative is that negative 1/2 e to the negative y squared. But remember, I need to tack on the z. So I have negative 1/2 z e to the negative y squared, and y is going from 0 to z, and that gives me negative 1/2 z e to the negative z squared plus 1/2 z. Okay, we end up having another u sub. There really isn't a great way to avoid this. Notice that this, because of e, there's kind of this pattern here. This u sub is going to be identical to what we did here, so I'm not going to repeat it because we can use the same format that we did up here for y. It's the same process. Remember, the negative 1/2 will just kind of tack on to the front, but the same process is what we did up here. So I'm not going to redo that. I hope that's okay. The antiderivative will be 1/4 e to the negative z squared. The antiderivative of this guy obviously is just power rule, so that's going to be 1/4 z squared. And we're evaluating this from 0 to 1, so we get 1/4 e to the negative first plus 1/4 minus 1/4, and so our final answer would be 1/4 times e. Okay, here is a nice summary of the different types. We have not done a type 3 yet. We will in just a moment. So this kind of gives us you a visual as well as just the format of each of the types. So again, you're focused on that internal variable. So obviously we could have either dz on the inside, dx on the inside, or dy on the inside. The rest of it, dA obviously is the rest of the variables. So, if you were to take, for instance, the type 3, which we haven't talked about quite yet, type 3 is dy on the inside. dA is going to be either dx dy, sorry, it's going to be either dx dz or dz dx. So that's the process. Remember, it has to do with the projection. So do you project it on the xy plane, the yz plane, or the xz plane? Okay, let's try the next problem. Oh, and sorry, one more kind of hint here is that, when you set up your type, it really boils down to there may be a type that is easier than another, and then you obviously want to go with the easier one. So just try to keep that in mind as you anti-differentiate. All right, let's try example 5. So this is written with dy on the inside, and so it is a type 3, and we're not going to change it. I'm not going to bother graphing it right now. Let's just try it. Okay, so our integral 0 to 1 and our integral 0 to z come first. We have the antiderivative with respect to y, which is 6xyz, and y goes from 0 to x plus z, like that. And we get 6x times x plus z times z, and I'm going to definitely simplify that. 6x squared z plus 6xz squared, and we have dx dz. All right, the next one, we have the integral 0 to 1, and now we have the antiderivative with respect to x, which is 2x to the third z plus 3x squared z squared, and x goes from 0 to z. That gives you 2z to the fourth plus 3z to the fourth equal to 5z to the fourth. And we do our last one. So the antiderivative would be z to the fifth and evaluated from 0 to 1, and so we get an answer of 1. Okay, let's try example 6, and this is going to conclude this video. And the reason is that the applications are next. There's 2 problems on that we will do together. Those won't be part of the video. And so this is our last one here, and it certainly is the most complex because it's left a little bit broader. This is what we'll be getting into now with applications, as well as getting into with the last 2 sections of the chapter is, okay, what if it's not set up for us? How do we properly set this up to make some sense? Okay, so we have to choose the best order, and we have this triple integral over E. E is the region bounded by the paraboloid, so you can see the paraboloid right here. Y equals x squared plus z squared, and the plane y equals 4. So remember, that's where it stops. Otherwise, this paraboloid would continue. So we stop it here at 4, and that's our region. You could label this E if you want. So this is the region E that we're integrating over. All right, so we're trying to figure out the best order of operations. Now, the picture here is drawn, and think about it this way: if you were to try to, let's say you were standing. I know this is not very formal. Let's say you were standing here and you were looking down, and you wanted to try to cast a shadow on the XY plane. That would be this graph right here. So you would see, you would take this region, you would kind of squish it down to the XY plane, and you would get a parabolic shape, and this region would be inside the parabola, and y equals 4. This would be, if we were to project it that way, a type 1 region, because that means that z would be on the innermost integral. And I'm going to write this one out for us. So let's see, I'll do it like this, I guess. So z would need to be, and this is the part that's relatively complicated. So when you're looking at your object right here, okay, z would be, if it's type 1, z would be the top half of this paraboloid and the bottom half. It would, again, we have to figure out how to border the 3-dimensional object with a function on the top and a function on the bottom with regard to the z-axis. So to do that, you would have to solve this for z, which is plus or minus the square root of y minus x squared. Now, that gives you the upper and lower boundary with regard to z. So this would be negative square root of y minus x squared. This would be positive square root y minus x squared. I'm going to go ahead and put the function in here. By the way, it looks like the function is related to the object, and it's, notice how this kind of looks like that. They have no relation to each other. Like this is the function f of x, y, z, and this is the paraboloid that we're integrating over. So I know that probably is really confusing, but they don't relate to each other at all. Okay, let's back up here. Okay, so that's going to be z. Now, if I go over here to my projection, y is in between x squared as a lower boundary and 4 as an upper boundary. So my next integral could be x squared to 4. So I've done dz, now I've done dy. And then x is, again, what's the left boundary and the right boundary? It's going to be from negative 2, I'll try that one last time, negative 2 to 2, like that. So this would be a type 1 region. Now, and then this is going to be dx. Now, the reason that this is not a wise one to choose is because how do I do the antiderivative of this with respect to z? That is going to be probably too tricky, right? And so because of that, just because of that reason alone, we don't really want to pick a type 1 region. So why did I torture you through that? I want to make sure you know how to set them up in any kind of type. And so this is not the type we want to use because the antiderivative is not really possible right now. So we're going to choose a different type. So I'm going to try to use type 3, which means that I border it with y. Well, why would I do that? Well, because it's written that way, right? So y is already defined as our upper and lower boundaries of E. And so we're going to look at projecting this on the xz plane. So again, you're going to go through, let me try to erase some of this extra stuff here. So we want to look at the projection. If we were standing kind of over here and we were to look at it this way, the projection on the xz plane would be a circle, and the circle would be of radius 2. Now, how could you figure that out? Well, it's really a combination of our two equations. So if I was to just simply plug in 4 for y, I get my circle on the, let me write that correctly though. I get my circle on the xz plane, okay? So there's your region, it's gonna be right here. Okay, so in terms of an integral, what does that tell us? Well, the integral will be, I'm gonna put x on the outside. So x is between -2 and 2. You know, again, when you're looking at a circle, you need to make sure that you have the top portion of this, and then you need to have the bottom portion of this. And so remember, if z squared is equal to 4 minus x squared, z is equal to plus or minus the square root of 4 minus x squared, like that. So for z, I have negative root 4 minus x squared to 4 minus x squared, like that. Remember my y values, my minimum is the paraboloid, because that's going to border it. Sorry, technical difficulties. So that's going to be my minimum, and my maximum is going to be 4. So then, again, my function is here. So I have dy, that was my innermost integral, then I have dz, then I have dx. This will continue to take practice, okay? So, you know, we will continue to work on this and continue to, you know, reiterate what the order may be and just keep practicing, because it takes a lot of time. Okay, we're going to try to tackle this problem now, which is sort of easier said than done because it's kind of an ugly one. The antiderivative is actually reasonable. I'm going to write out these integrals first. Okay, so what we have is the antiderivative with respect to y, which thank goodness is pretty easy. It's just y times that. Y goes from something sort of ugly, though. It's going to go from x squared z squared plus z squared to y equals 4. So that gives us 4 times x squared plus z squared minus the quantity x squared plus z squared times the square root of x squared plus z squared. Okay, and we have dz dx. All right, really ugly. Okay, so let's think about this for a moment. We're down to a double integral now, and my double integral is really ugly, but notice how we have this x squared plus z squared behavior throughout. We're going to use the process of polars. This ultimately, with the triple integral, is called the use of cylindrical coordinates, which we will discuss in section 12.8. But keep in mind that polars are a nice placeholder for any type of behavior like what we're experiencing in this problem, where we have this circular region. But I don't want you to get confused. We've used polars with x and y because that's how our integrals are written. Pretend like y and z are sort of the same thing in this problem. You know, we're going to use polars, and we're going to use the relationship that r squared is going to equal x squared plus z squared. Additionally, and you can look at the object above, that circle that we're dealing with, we're going to let r go from 0 to 2 because we have this circle with 2. And again, forget the fact that it's the xz plane. We're just dealing with these variables together. And then theta is, of course, 0 to, is a full circle, so 0 to 2 pi. So here's our conversion, because again, we don't want to tackle this green equation. This looks awful to do an antiderivative. I don't even know how we would do it. So we have the integral from 0 to 2 pi. That's going to be theta. We have r, which is 0 to 2. And now let's go ahead and rewrite all of this stuff. So remember, we have 4 times the square root, and I'm going to save a little time here. It's the square root of x squared plus z squared, the square root of r squared, which is just r. So we have 4r minus x squared plus z squared is r, and the square root of r squared is just r. So I have, in other words, I have r squared, which I didn't write a square, I'm sorry, times r to the first. Now remember, don't forget, you got to add an r and then dr d theta. I'm going to rewrite this and simplify before we analyze it. So I have 0 to 2 pi, I have 0 to 2, I have 4r squared minus minus r to the fourth dr d theta. Okay, well, we know that we can take that 0 to 2 pi. We've done this a bunch of times, so I'm not going to get into that too much. We did that in 12.4 a whole lot. So we have 0 to 2 pi of d theta, that's just 2 pi, times the antiderivative, so 4/3 r cubed minus 1/5 r to the fifth from 0 to 2. That gives us 32 over 3 minus 32 over 5. And I'm just simplifying with a calculator to get 64 over 15. So then if you take that multiplied by 2 pi, you get 128 pi over 15, and that is finally it for this one. Okay, so again, remember the last couple examples are applications. We will do those together in class. Thank you.